All right, we should get the lecture started. Hello, everyone. Welcome to lecture 15 of the Differential Privacy course. And today, we're going to be talking about the second algorithm under the category of data adaptive or data dependent differentially private algorithm design. So this family is called proposed test release. So we'll talk about what it is and what's its pros and cons relative to smooth sensitivity framework. Okay, so before we get to the lectures, so notice that the official deadline for the second homework is due today. You guys have a few days of grace period. So you should submit the homework too as soon as you can. The coding part in particular, like after I provided that template, it should be just a straightforward slot fill in. So just implement a small part of the code and then everything should run. So if you run into trouble with that, please let me know. And if you spot any issues in the code template, and if you observe something that doesn't quite make sense, and please also alert me. Yeah, because I've tested it for a few times, but maybe there's still some like small issues that's in the code. I didn't exhaustively try out like what happens if one part of the code is implemented wrongly, or whether you'll see things that are sensible. So for the interest of giving you enough time to do your course project, so homework 3 will be lightweighted. So I'll try to make it much shorter comparing to homework 1 and 2. Homework 1 and 2 are not that long, but homework 3 will be shorter than 1 and 2. Yeah, but each question, on the other hand, will carry more weights since we're doing even weighting for all the 3 homeworks. All right, so let's get to the lecture. So last time we started the new chapter on going beyond the worst case noise in differentially private algorithm design, and we talked about differentially private query release. And as a recap, so the key concept in differentially private query release is to calibrate the noise with a scale parameter proportional to the sensitivity of the query itself. So the global sensitivity or GS of this query, let's say X is the data size, just defined to be the maximum absolute value difference between the 2 possible neighboring data set, right? So it could be absolute value or sometimes L2, L1 sensitivity, L1 sensitivity for the Laplace case, L2 sensitivity for the Gaussian mechanism case. But what we've seen with the examples in the last lecture is that the global sensitivity can sometimes be way too large for this noise adding approach to make any sense, for you to return anything that's useful in practice. The example that we gave was median, right? So there always exists a somewhat pathological data set that the median, after we just add or replace one individual data point, and then the median can go from the smallest possible in the domain to the largest possible in the domain. And that motivated us to consider adding noise proportional to local sensitivity, where the local sensitivity condition on the current data set, right? So it makes a local perturbation to the current data set by replacing one data point or adding or removing one data point, and then you can define local sensitivity this way. So this allows us to consider only the local neighborhood of X, but what we've seen is that adding noise with magnitude proportional to the local sensitivity doesn't give us differential privacy. And the issue is that the local sensitivity itself might be unstable. So as we change from X to X prime, as the local sensitivity also changes accordingly, then we might be adding a substantially larger noise than what we're adding at the current location. So the magnitude of the noise itself will reveal the sensitive information and allow an attacker to identify whether the data set is X or X prime. And that is resolved by finding some kind of a smooth upper bound of the local sensitivity of the following form. So the smooth sensitivity with a parameter beta is a is an upper bound of the local sensitivity. It's upper bound of the local sensitivity, and also the makes all other data point and the local sensitivity of this alternative data point by multiply with e to the power of minus beta times the distance between x and x double prime. Okay, so that's the yeah, that's a definition of smooth sensitivity. And the idea of smooth sensitivity is that if we add noise according to the smooth sensitivity, and this smoothing property ensures that this smoothing property ensures that while we stay as a valid upper bound of the local sensitivity, but on the other hand, like the noise, the magnitude of noise will not change that substantially across two neighboring data set. Therefore, that allows us to bound some discrepancy measure between the two distributions on any two neighboring data sets. So it's a very natural idea. So the issue about local sensitivity is that itself is not the local sensitivity itself can be highly sensitive, and the smooth sensitivity addresses this problem by algorithmically smoothing the distribution of the noise that we add, no matter what the local sensitivity is. So in those cases, when the local sensitivity itself is already smooth, then the smooth sensitivity is going to be very similar to local sensitivity. And in those cases, when the local sensitivity is spiky and it changes drastically across individual data points, then adding noise proportional to smooth sensitivity will add slightly larger noise in the than that of the local sensitivity, but it addresses the issue that makes this idea infeasible. Okay, so we talk about what are the noise that are admissible to use for the smooth sensitivity framework. So we require so any noise that satisfies two properties, so sliding property and dilation property, which effectively says that if you do a like translation of the noise distribution or slide it across its domain by some bounded delta towards any direction, then it satisfies this epsilon delta indistinguishability property, right? Something that epsilon delta dp. And in addition, if you multiply this noise by a multiplicative constant of e to the power of lambda for some small lambda, lambda smaller than beta, let's say that this lambda and beta is a smoothing property of the beta smooth sensitivity. So when beta is small, then this is saying that I'm just multiplying something that's 1.05 or something to the noise, and with the scaling it's called dilation or scaling, and scaling of the noise, it doesn't really change the noise too significantly. So that's a dilation property, and it follows the same notion of epsilon delta indistinguishability. If both these two conditions are true, then we can just add noise proportional to with magnitude proportional to the smooth sensitivity, with its alpha chosen appropriately, and beta being the smoothing parameter of this S of the smooth sensitivity, and altogether this algorithm satisfies epsilon delta dp. Okay, and we've seen the analysis of how this works in the last lecture, and the idea really is similar to group composition, in which case we decompose the noise adding procedure into two phases. In the first phase, we use a sliding property to bound the difference, and in the second phase, we use the dilation property to bound the difference. So altogether, it gives us epsilon delta dp. And yeah, so there was a little glitch in how the paper presented the proof of this theorem, which I followed a simple proof, and at the end of the day, I think what you get is epsilon and e to the power of epsilon plus 1 bracket delta dp. So rather than the over 2 dp, rather than the epsilon delta dp as claimed. So I believe this epsilon delta dp claim is true, but it requires a slightly more complicated argument. So then we move on to talk about what are some of the other noises that satisfy, what are some concrete noises that satisfy these properties and beyond. And we look at this paper, recent paper by Bond and Stanke, which proposes several other practical noise distributions to use under the smooth sensitivity framework. So far here is a summary of our knowledge about smooth sensitivity. So we know that if we add really heavy tail distribution like Cauchy distribution and student T distribution, and this gives us a pure differential privacy. And if we add things like Laplace log normal distribution or uniform log normal distribution. So we'll revisit what Laplace log normal is in just the next slide. But this gives us the role concentrated differential privacy, zero-centered concentrated differential privacy. And suppose we add the typical noise that we add, like it also works, but it works slightly, it produces a slightly weaker differential privacy guarantee. So it gives us approximate epsilon delta dp with delta larger than 0. Okay, so most typical noises work, and some work better than others. Say if we have this concentrated differential privacy bond, then we can make use of it and then concatenate this and compose this with other mechanisms that satisfy Renyi differential privacy or concentrated differential privacy, which gives us algorithms that are substantially more practical.
I wanted to ask,
yes.
So, when you have like a Laplace distribution, it's not really the same as the identity each coordinate Laplace. Because I'm assuming here that because in the previous slide, it's like you have to.
Yeah, you are still adding the Laplace noise to every coordinate. The difference is that now you are not adding the noise with magnitude proportional to the global sensitivity, but rather you are adding noise with magnitude proportional to the smooth sensitivity. And in the multivariate case, this smooth sensitivity needs to be worked out for the multivariate output of this f of x.
But then here the Laplace distribution is like symmetric.
Here the Laplace distribution is symmetric. It's symmetric to every coordinate, and you are using the same noise in the smooth sensitivity case. Yeah, so the Laplace noise is not isotropic. So if you rotate the output space of f of x, then you get something that's very different. But for the Gaussian noise, it's isotropic. Then when you rotate it, and then you get the same IID Gaussian noise. Yeah, if that's what you're asking. So. Okay, yeah, you can find me at a break if it doesn't address your question. So let's take a closer look at what the Laplace log normal distribution look like. So this is really the combination of two noises that we know dearly in differential privacy. So the idea is that we add noise z, and this z can be generated by drawing this multiplier x from a Laplace distribution, and then draw this y from the standard normal distribution. And this sigma is a tuning parameter. And the idea is that if we add noise according to the Laplace log normal distribution, then yeah. So first of all, what is the intuition here? So in this, like the intuition is that we are smoothing out the scale of this Laplace distribution with a Gaussian distribution, right? So this Gaussian distribution, e to the power of something. So this log normal is always since it is e to the power of something, it is always non-negative. It has some expected value. But what this is doing is to say that condition on each y, it picks a particular magnitude for x. Right? So sometimes it is smaller than its mean, in other times it's bigger than the mean. But this is what provides something that resembles the dilation property, as we'll see later. But the idea is that like now it's supposed to add Laplace log normal distribution with magnitude proportional to the smooth sensitivity with parameter t, and then like this satisfies a concentrated differential privacy with parameter being half epsilon square, with this epsilon being this quantity. Okay, so the proof is actually not that crazy. So in today's lecture, we'll finish talking about the concentrated differential privacy analysis of the smooth sensitivity for the Laplace log normal noise, and then I'll show you some empirical results to demonstrate that this is something that actually works and is doing things that are data dependent, like gives you a substantial edge over adenoids with proportional to global sensitivity. And then we'll move on to talk about the proposed test release and other easy to use recipes that follows a proposed test release like ideas with several examples throughout the lecture. Okay, so for the PTR part of the lecture, we'll be mostly following the Salio-Vatans textbook on the complexity of differential privacy. And the original paper of Dork and Jinlei on differential privacy and robust statistics is the first paper that describes the PTR idea. Though the particular paper is not the easiest to read, and the example that they gave is somewhat not mainstream. And then this other paper that I give in the end gives an excellent example of how you generalize the PTR idea to derive something for differentially private machine learning. So yeah, we'll see a bit of these, and but mostly focus on the Vatans book section 3.2 to 3.4. All right, so back to concentrated DP of the smooth sensitivity. So recall that we're adding this Laplace log normal noise when X is drawn from a Laplace distribution and Y is coming from a standard Gaussian distribution. And how do we analyze this, and how do we show that this is satisfied this concentrated differential privacy? So in particular, like in order to bound the concentrated differential privacy, we need to bound the Renyi divergence of two neighboring data set, right? The Renyi divergence of two neighboring data sets. So this is on data set, say on data set X, the output is f of X plus say G of, so let's say this G of X is a smooth sensitivity scaled with this 1 over S. So this is some multiplier to this noise Z. So this is the algorithm for this is the algorithm on the dataset X, right? So this alternative the algorithm will output f X prime plus, very importantly, the noise multiplier. So this is the 1 over S multiplier with a smooth sensitivity is a function of the data itself, right? So this is a function of the data itself, and all we want to do is to calculate the alpha's Renyi divergence of these two distributions. So maybe let's simplify this a little bit so that we can get away with just working on like two noise distribution alone rather than dealing with f and fx prime. So what we can do is to well, let's first move this f of x to the other side, right? So this becomes fx prime minus f of x plus g x prime z, and on the left hand side on the left hand side, we just have gx times z as well. Okay, and so this is equal. I'm just moving a constant like this corresponds to shifting the distribution by the same quantity, shifting both distribution. So next, I'm gonna divide both sides by g of x. So this is also not going to affect the distribution because it's just applying a matter of scaling, and gx is a fixed constant in this case, since both x and x prime they are fixed. So I can divide both sides by g of x, and then this gives me the Renyi divergence of z, the noise z itself, fx prime minus f of x over g of x plus gx prime over g of x multiplied with z. Okay, so now this becomes something that's familiar to us, right? So now this becomes something that's about the noise on the left hand side, and another noise that is dilated and translated. Dilation and translation. So basically, in order to prove the ZCDP property, it requires us to get the dilation and translation property of these individual of the noise distribution itself. In this case, the Laplace log normal distribution. Wait. Okay, so now we have this. The next thing to do is to replace these data dependent quantities with just data independent quantities. So what I guess let's call this S. By the way, by the definition, like X and X prime being a neighboring data set, the fact that the Gx is the upper bound of the local sensitivity ensures that the difference over G is bounded between, so this is bounded between -1 and 1, right? So multiply with S, the whole thing is bounded between -S and S. Moreover, this Gx prime over Gx, so by the fact that the global the smooth sensitivity is smooth, so this shows that this Gx prime is sandwiched in between the e to the power of t and e to the power of -t of the G applying to its neighbor, right? So we know that this quantity is bounded from above and below by e to the power of t and e to the power of minus t, right? So with these two, we have reduced the problem to bounding the max of two concrete Rényi divergence, which is z s plus e to the t e, and if we just toggle the two, s plus e. Okay, yeah, so it becomes bounding these two like these two Rényi divergences. Okay, and how do we and how do we do that? And so the idea of bounding these two is to find some intermediate distributions, such as we can decompose this Rényi divergence calculation into, say, some kind of a triangular inequality, so that we can apply the dilation properties and translation property to each one of these to each one of the component in the decomposition, right? So for this, we'll make use of these particular theorem about Rényi divergences that applies to the cases when each one of these Rényi divergences satisfy a linear upper bound. So let's read this lemma together. So we want to find some probability distribution R that sits in between P and Q, and then use it to upper bound the Rényi divergence of P and Q, right? So no matter what R to choose, if we can show that this Rényi divergence of P and R is in some sense satisfy a CDP, so this is upper bounded by a linear function. And similarly, if dA of R at Q is also bounded by a linear function, so in this case the parameter is B, then it can be shown that the Rényi divergence of PQ is smaller than it also satisfies a Rényi divergence bound like this. So this is saying that A CDP and B CDP, and if we just compose them, so it's not the same as the composition of mechanism, because this is trying to do the group privacy, and we want to calculate the Rényi divergence between P and Q. Then then these two together implies the square root of A plus square root of B square CDP for PQ. And this is PR. This is RQ. So notice the order does matter here, right? The order of the distribution does matter here because these are divergences rather than distance functions. It doesn't satisfy the when you swap P and Q, then you still get the same number. Yeah, which is what makes these divergences, and the part of the reason why we need to bound these two things separately. So what is this particular? So we'll be choosing Z to be P and this E to the power of and this quantity to be Q. So we'll be choosing this to be P and this to be Q. And the question is that what is this R that we should be using? Okay, so the argument the argument is the following. So let's try applying some of the algebra of these divergences by changing the distribution slightly again. So we can first move this plus S because it's a constant to the left hand side. So this is the minus S e to the power of T Z. Okay, so once we do this, we can decompose this into we can call this P and call this Q, and then we can define R to be just Z, right? We can define R to be just Z, and we know that this is smaller than then it suffices to bound minus S Z and D alpha and Z given e to the power of Z, right? It suffices to bound these two. And show that these two satisfy some kind of linear upper bound B times alpha, and then these two together would imply that this quantity satisfies square root of A plus square root of B square multiplied with alpha. Okay, so this reduces the problem to just translation only and dilation only, right? And their corresponding Rényi divergence calculations. Yeah, so I'll skip the second part of it because it's really the same. Because it's really the same. But I hope this convinces you that now it suffices for us to show that what are these quantity A and B by handling the translation of this minus S and the dilation of this multiplying by e to the power of T separately. Right. So that's given by these two lemmas. So let me tell you a bit about the intuition of these two lemmas and give you a sketch of the proof for each. We'll start with the dilation property. So what is the distribution of Z again? So Z is a distribution when X is drawn from a Laplace distribution and Y is drawn from a Gaussian distribution. And in order to show the dilation property, it suffices for us to condition on individual X, right? And the first inequality, like technically this is so due to so-called quasi-convexity of the Rényi divergence. Yeah, so due to the quasi-convexity, and we can take the soup over these individual quantities. Like let's say suppose you have convexity, and then you can then you can in some sense replace this soup with some form of an expectation, because here the X is inside. If you pull the expectation out, if you pull this X out, the expectation over this X out, and then you can apply the law of total expectation to condition on every X, and then if it suffices to bound. Yeah, so the idea is that in order to bound the Rényi divergence of these two distributions, it suffices to fix every individual X, and then bound the corresponding Rényi divergence of just this log normal distribution. Yeah, without worrying about what this X is. Suppose for every X we can have this bound, then that implies an upper bound of this quantity that we're interested in controlling, right? And technically, this uses the quasi-convexity of the Rényi divergence. And now the problem reduces to this. And the second part of the argument is to say that, oh, let's fix each x. And what is this distribution? It's log normal. And log normal is, well, the log normal distribution is a post-processing of the normal distribution. Right, so it's applying the output of the normal distribution with an exponential transformation. And by the fact that by the information processing inequality, like in the differential privacy sense, this is called closure to post-processing, then we can bound the post-processed outcome with that of the outcome of the normal distribution itself before the post-processing. Okay, so this is by the information processing inequality or post-processing, closure to post-processing. And then this becomes something that's already familiar to us. So sigma times y is a 2 Gaussian distribution. So this is a Gaussian distribution on data set x, and this is a Gaussian distribution on data set x prime, when f of x and f of x prime is smaller than t. Right, and we know that this is a Rényi divergence of this Rényi divergence satisfies the concentrated differential privacy, and this is smaller than just 2 sigma square alpha t square, and t is a sensitivity, and the sigma square is a noise that you add, and this is a CDP parameter for the Gaussian distribution. How about the other leg? How about the translation property? Yeah, so the translation property looks like this. And I won't go into the details of the proof, but the idea is about calculating the log density ratio, and show that with probability 1, this log density ratio is bounded. Is bounded by e to the power of 2/3 sigma square times s. Okay, so when are these like log density ratio bounded? This is when it satisfies pure differential privacy. So in particular, for this one, we're essentially showing that the translation properties satisfy the epsilon differential privacy, and using the fact that this x distribution is drawn from Laplace distribution, right? So having this e to the power of sigma y, when y is a Gaussian, that complicates the analysis a little bit, but the idea is just to show that the log density ratio is smaller than the constant. And with that bounded, the Rényi divergence is straightforward. So because since this is always bounded, then you can take alpha to infinity, and this is an upper bound of the pure DP parameter, or the Rényi divergence parameter when alpha is infinity. And then similarly, when alpha is small, then you know that any pure DP mechanism, so any epsilon DP mechanism, satisfy half epsilon square CDP. Right, that gives you this linear upper bound of this form. Yeah, so half an epsilon square, and you got this particular epsilon square. Right, so by combining these two together, and you can see that, and this becomes this t square over 2 sigma. So this is what we define as A, and then this half e to the power of 3 sigma square s square, this is what we define as B. And if you combine these two together and then apply this lemma in the previous page, then we can get that the overall is satisfy the concentrated differential privacy with this parameter, like as we previously claimed there. All right, so that's really the analysis of a concentrated differential privacy of this log normal distribution. Laplace log normal distribution for under the smooth sensitivity framework. So here's a illustration of how it works in practice on a particular example. So the problem that we consider now is so-called trimmed mean or robustified mean. So the idea is that you sort your sequence of numbers. So instead of calculating mean, you want to make your estimator more robust to the outliers, right? So what you do is that you take the largest, you take the largest m, you take the smallest m, and then compute the average for everything in the middle, right? So this kind of robust estimation has like a century of use in various applications, and maybe if you watch Olympics, that you see that in all those diving competitions, and people are removing the highest score and lowest score and then compute everything in the middle. So that's an application of this trimmed mean, right? So so it's something that people use in practice even out of the context of differential privacy. But for the interest of differential privacy, trimmed mean has the benefit of allowing your algorithm to not depend on the largest perturbation due to outliers. Okay, so in this case, the range is somewhat large, therefore the global sensitivity is kind of large. So the global sensitivity would be the range over the number of data points. But the local sensitivity can actually be quite small, because now that you've removed this top m and the largest m and the smallest m. Because if you add anything that are larger than the, say, the m's larger than the n minus m quantile of the data set, then we won't have any effect, right? So therefore the local sensitivity can be small, and then we can derive the smooth sensitivity algorithm for releasing the trim mean. Okay, what Bond and Steinke have shown is that this blue line is a Laplace log normal with a parameter 0.5 on this CDP parameter, and the non-private version of the trim mean is this line, right? So as you increase m, right, you see that the variance, yeah, you see that the variance of the estimator gets slightly worse even for the non-private algorithm. But as m increases, the performance of the differentially private algorithm and like the non-differentially private algorithm, they somehow get closer and closer. And by comparing these lines, then you can actually find like how much better that one can get from one to how much additional cost that we need to pay in terms of variance when we want differential privacy. And so notice that n equals to just 200 is extremely small, right? So in this, such a small data set, the impact of privacy is quite substantial. As we can see that what is the best choice of differential privacy? So it's when we choose m that is almost half of the data point, so that we can remove a lot of the outliers. And in this case, the differentially private algorithm achieves something with variance multiply n minus 1 that are like smaller than 1. So it's quite remarkable, and it's not too far that within a magnitude, an order of magnitude from the best possible solution of the trim mean estimator. Of the trim mean estimator at say m equals to 20. Yeah, of course, when you do not require when you do not require robustness and just calculate the mean, so that is when this dashed line of this non-private version of the estimator converges to the smallest possible value. So this is just simple average. Then you get results that are substantially better. Yeah, the issue is that you're also losing the robustness of the problem. When we increase the number of data points to 1,000, then you can see that even when this m is chosen to be relatively small, then all these smooth sensitivity based algorithm is doing quite close to that of the their non-private counterpart. And I also wanted to show the comparison with the noise adding approach that calibrate noise according to global sensitivity. So these are like these two dashed lines, right? You can see that these two dashed lines, like they don't really like they don't really work very well unless we trim the unless we trim it pretty substantially. So up to say m equals to 200 and 300 before these two converges to in the same ballpark to everything else. Okay, so that like for more details, like you guys should check out this paper itself. It's quite a nice paper, and yeah. All right, so I wanted to so that wraps up our discussion on smooth sensitivity. So I wanted to mention a few limitations of the smooth sensitivity framework. So even though it is quite elegant, it uses an idea that directly address the issue for the problem of differentially private query release, but it's not very widely applicable beyond the context of differentially private query release. So specifically, like the method is restricted to just outputting the numerical values. So these queries that output numerical values. So things like exponential mechanism, which the goal is to find the argmax when the space that you select from can be abstract and arbitrary. So smooth sensitivity framework doesn't work there. It also requires very careful design of the noise and often a very heavy-tailed noise like Cauchy distribution, student T distribution to achieve very strong privacy guarantee. Like we didn't talk about high dimensionality, but if you stare at the dilation and translation properties of, say, the Laplace noise, Gaussian noise, and also this more carefully designed noise, then you will realize that these methods do not really generalize well to high dimension. So when the dimensionality is like 10, 20, then the kind of benefit that's coming from like leveraging the local and smooth sensitivity becomes more or less negligible. So yeah, so I guess the key intuition is that in high dimensional space, so everything that seems to be far apart is actually also very close to each other, and the distance, like you do not really get that much of a benefit with that e to the power of minus beta. Yeah, so I won't go into details there, but you can get a sense of that by looking at the dilation and translation properties that's derived in the original paper on smooth sensitivity. Yeah, so all these limitations motivate us to consider whether there are other like flexible recipes or flexible framework for designing the data adaptive differentially private algorithms that doesn't rely on smooth sensitivity, at least not directly. So I'll give an example on when smooth sensitivity, like even smooth sensitivity doesn't actually exist. But we can actually hope to do something good there. So let's say that this f of d be a counting query. So calculating the number of students with grade larger than a minus, a minus. And then we can also define like this artificial query, which is also just a reciprocal of this. So g of d is 1 over this f of x. So now here are the questions to you. So what are the global and local sensitivity of this g of d? Yeah, and anyone? So f is just a counting query, and d can be arbitrary. Then what is the global and local sensitivity of GD? How about we start with global? Like what is the worst possible perturbation that you can have here? Yeah, excellent. So when f of d is equal to 1, then you get 1, and when f of d is equal to 0, which you can achieve by just adding or removing one individual data point, and then it suddenly becomes infinity, right? So the global sensitivity is not bounded. How about the local sensitivity? 1 over fd minus 1 over fd minus 1, right? Absolute value, right? So that's the local sensitivity of g of d. So excellent. So basically, whenever f of d is larger than 1, whenever we know that it is larger than 1, then we can bound this by something that's quite small. And when fd is large, and we can even bound this by something that's on the order of 1 over f of d, right? So suppose we're only adding noise to a local sensitivity, then we don't actually have to add a whole lot of noise, right? So this f of d is a summation. It can be proportional to the size of the data set. But how about the smooth sensitivity here? Because the global sensitivity is a plus infinity, and any data set, like we can always swap it up to n steps towards towards something that's completely zero. So you'll end up getting to this local sensitivity of this pathological data set where f of this is equal to 0, right? So when you have this, taking e to the power of minus n beta for any beta multiplied with infinity, multiplied with infinity will always give you infinity. Right. So for these reasons, this is an example where the smooth sensitivity doesn't actually exist at all. Okay. On the other hand, like there's obvious methods that we can try reporting things that are interesting, like for this problem. So we can simply privately release f of d, and then somehow construct a lower bound of this f of d, and then we can somehow construct confidence bound of this gd in a differentially private fashion. Right, but just using the smooth sensitivity framework, we cannot like directly add noise to g of d to achieve the same goal. Okay, so this may appear to be like a contrived example, but I argue that calculating the reciprocal is often needed and sometimes quite useful in machine learning and statistical application. Let's say that suppose we have a linear regression model, and we can estimate this theta hat from the data. So let's say that this is x transpose x inverse x transpose y, right? And then let's say that we get this from a public data, and then now we want to do the uncertainty quantification by quantifying. Let's say that there's a new x tilde, and then I'd like to know how close is this to this x tilde transpose x star, when x star is the true coefficients that actually generates the data. So this kind of a variance or standard deviation of the difference of these two is proportional to so this is this is proportional to x tilde square root of x tilde x transpose x inverse x, right? So in the middle, you can see that this is a matrix inverse, and that's when you have this when this x is a private data set that we're talking about, and in order to release this value, it requires us to release a particular projection of the reciprocal of this inverse covariance matrix. Okay, so another example is a private argmax. Let's say that since this is argmax, the output is not numerical at all, right? So it could be in the problem of voting, which we've seen quite a bit now. So there are Trump and Biden, and suppose the people who participate in the poll, we're collecting their data set, but wanted to preserve differential privacy. And then we wanted to know who won the election in the end by releasing the argmax differentially privately, right? So we cannot just add noise to trump because it's not a numerical value, of course we can just directly use Laplace or Gaussian mechanism to release the histogram of the votes, but that's different from just getting the argmax itself. Similarly, we can consider the problem of model selection. Let's say that we have a private holdout data set. We have a private test data set, and you are given n different machine learning models, and you just want to evaluate these models on the private data set and then output the one that is the best, right? For this task, it also doesn't quite make sense to add noise to the machine learning model itself, because the model can be completely abstract and it might not like even make sense to add noise to the model. Let's say that these models can be decision trees. They can be random forests. And how do you add noise to a random forest? And then still ensure that after adding noise, it remains a particular random forest. And in addition, say takes the problem of Netflix. So Netflix wants to show on your TV that here are the most popular movies, but these popularity scores are computed based on their viewing histories, and the viewing history is contributed from their users' data, and their users' data are supposed to be kept differentially privately, right? So what Netflix can do is to try privately releasing the top max, top K, right? So this is the let's say that there are like in total of n movies. So this is the choosing the argmax from any subset with a subset size smaller than equal to K from the set of n choose K candidates such that it maximizes the popularity score. Popularity, I guess, the sum of individual as in this, right? Some kind of popularity score. Right, for this one, like we also don't know how to make use of smooth sensitivity to adapt to situations where like I can do this better than simply running say report noisy max or running exponential mechanism. Okay, so I'll talk about like one solution to this problem. So the idea is that the argmax can be quite stable, right? Suppose the argmax is substantially better than the second best choice, then hopefully we can leverage this information of large margin in this differential privacy selection problem. And the point is that if that happens, we don't even have to add noise at all. So this is a very cute idea called leveraging the stability of the query. So this is about releasing stable values and with the value being completely like arbitrary. It doesn't have to be numerical values. It can be, yes, it can really be like arbitrary it can really sit in the arbitrary space. So let me explain this idea. So first of all, let's define a function called the distance to instability. Okay, so distance to instability. So I'll call this the D function of data set X. So the distance to instability function is the X is a smallest distance of X with X double prime such that X double prime satisfies that f of X double prime is different from f of X. Okay, so this is the distance to, so this measures that how many data points that you have to add or remove from X in order to obtain, yeah, so this is somewhat tricky, so pay close attention. So this means how many steps, how many data points you need to add or remove before x can be made into x prime, x double prime, such that x double prime's output is different from f of x. So f is a query that we want to release, some function of the data, and the function of the data, like say it could be argmax, it could be finding the top K most popular movie, and x prime and x, they are data sets. They are data sets, the user statistics, their viewing history, and so on. So how many users do I have to add or remove in order for me to change the top K most popular movie, say within the past weeks, right? So this is a critical function called distance to instability. So you are currently at x, like adding or removing one individual doesn't actually change f of x at all. So the local sensitivity of f of x is 0. But moreover, like among all the data sets that are 2 steps away, the local sensitivity is also 0. Among all the data sets that are 3 steps away, the local sensitivity is also 0. So you need to go all the way to this d of x, so distance to instability, before before this modification to your data set actually changes the output of this query f. So the distance to instability mechanism is also straightforwardly stated, which leverages this d of x. And so observe that this d of x is d of x itself is a function with bounded global sensitivity. So if the closest data point, a data set from x requires you to jump k times in order to make fx different, then changing x to be x prime, where x prime is a neighbor, is only going to at most make the distance to instability like d minus 1 or d plus 1, right? So this function, dx function, is 1 insensitive, or the global sensitivity of d, gs of d is gs of d is 1. Okay, so the mechanism will do the following. So the first, let's add noise to this distance to instability. So d hat is equal to d of x plus the Laplace noise 1 over epsilon. Okay, so that's the first step. And the second step says that if this d hat is larger than log 1 over delta over epsilon, then output f of x. Else, or d prime smaller than log 1 over delta over epsilon, then output nothing. Output, we use this symbol to denote nothing, right? So the idea is that basically I'm testing, or I'm checking whether whether I'm sufficiently far away from being unstable, being unstable. So if x is like very stable and in a large neighborhood, and if the neighborhood is larger than this quantity, then I'm gonna just output my exact value without adding noise at all. On the other hand, if this d hat is small, then I'm gonna be just refuse to answer the question. Okay, so is the idea of distance to instability clear to everybody? So I'll show you in the next slides how this is epsilon delta differentially private. Okay, so yeah, first of all, is the definition of the function distance to instability clear to people? So how many steps you have to jump by adding or removing data points in order for you to get to somewhere with an alternative data set x double prime, such that f double prime is different from f of x. Okay, and this function is 1, has a global sensitivity of 1. Okay, so now let's try analyzing this distance to instability algorithm. So by discussing two cases. So in case one, when this distance to when this d function is equal to 0. Okay, so this case when d function is equal to 0. So interestingly, when d of x is equal to 0, then for any neighboring x prime that is a neighbor of x, d of x prime is also equal to 0. Why is that the case? So let's maybe try calculating this d of x prime. So d of x prime is a closest that you get, which changes your exist neighbor x prime such that wait, is it exist? Yeah, actually it's any neighbor. So d of x prime, like you can just find you can basically just find x, because by definition this is saying that this is maximum of the distance of x prime, x double prime, such that f x double prime and f x prime, they are different. For any x being a neighbor of x such that, yeah, so let me add a clause, such that f x prime is not equal to f of x, then the distance to instability is also 0. And this is clear because when we do this, I can choose x double prime to be x. I can choose x double prime to be x, and then the distance, the number of jump will be 1. But that's not, wait, that's not how distance to instability is defined. Yeah, sorry guys, I think I wrote the definition wrong. So the definition should actually be this dx x double prime minus 1 and the minimum of this and 0. So if it takes one step for if it takes one step for this x to be modified into something that with x double prime is different, then it means that the local sensitivity of x is already non-zero. So let me patch this definition of this distance to instability function. So this is for you to search over all data sets that such that f double prime and x is different, and then I'm taking the I'm taking the max outside. So this function is non-negative, and then I'm taking the smallest x prime such that I reach something where fx is different, minus 1, and then since this could make it this could make it negative, then I'm taking the larger of 0 and this quantity. So can this be negative? It couldn't be negative because when dx and x double prime is 0, it means x prime is equal to x. Okay, so I don't need this. I don't need this max outside. So I can simply use this as a valid definition. Okay, so now back to back to the first of all, everything is still true, right? This d of x is 1 insensitive because the global sensitivity of that is still 1. And now let's look at the let's look at this case 1. So when d of x is equal to 0, then it means that for any neighbor of x, is d of x prime is also equal to 0. Because this implies that there exists an x double prime, such that d of x double prime is smaller than 1, and also fx is different from x double prime. And now if we consider if x is a neighbor, so d of x and x double prime is a neighbor, for this x prime being a neighbor, then the distance to instability dx prime is equal to the minimum of right, is equal to this. So if f of x prime is equal to x, then if x prime f of x prime is equal to f of x, then we can take x double prime. We can take x double prime to be part of this minimum. And if fx prime is not equal to f of x, then that itself has already indicated that this dx prime is equal to 0. Right. So when x is 0, has a value of distance to instability being 0, then for any neighbors of x, it is also 0. And for this reason, then under this case 1, so we're discussing the neighboring data sets when x and x prime are neighbors, and both of them have distance to instability being 1, and I'm basically adding noise adding Laplace noise of 1 over epsilon. So on the x and on the x prime, I'm also adding noise 0 plus Laplace noise. And the output is identical. The output is identical except when this Laplace 1 over epsilon absolute value is, I don't think they're absolute, unless this is larger than our predefined threshold, log 1 over delta over epsilon. And this happens with a probability smaller than delta. Okay, so in the case A, effectively, we've seen that this is 0 delta dp. Now let's go to case B. So this is when d of x is not 0, right? So when d of x is not 0, then when d of x is not 0, then f of x is equal to f of x prime for any x prime such that x prime and x are neighbor. Why is that the case? Because when the distance to instability is not 0, it means that I can move like one step away from me, and then the f the function evaluation is still exactly the same. Like for any such x prime. which means that which means that we need to discuss the two cases, and the first case is the output is perp, and the second case is output is f of x, because f of x is the same as f of x prime. So when the output is perp, this is a post-processing of a Laplace mechanism. Laplace mechanism of d hat is equal to d of x plus Laplace 1 over epsilon. Because I'm simply taking this value and then threshold this at a particular threshold, and that gives me the condition that I'm going to output tilde. And similarly, like this is also like a post processing of this. So basically, when d hat is when d hat is larger than log 1 over delta over epsilon, I'm outputting this. When d hat is smaller than log 1 over delta over epsilon, I'm outputting f of x. So the output space is binary. So it could be either perp or f of x. And because of this binary output, and then the binary output depends only on a post-processing of this output of the Laplace mechanism, then we know that in case B, it satisfies epsilon dp. So in one of the cases, we satisfy 0 delta dp. In other cases, we satisfy the epsilon 0 dp. So in total, altogether, this algorithm satisfies epsilon delta dp. Okay, so recall that epsilon delta dp requires is an upper bound that is required to hold for any two neighboring data set x and x prime. So this is a case when x and x prime satisfy the d of x is equal to 0, then it satisfies 0 delta dp. And in the alternative case, when x and x prime that when dx is not equal to 0, then it satisfies pure dp. So altogether, both of them satisfy epsilon delta dp, which concludes the analysis. Yeah, it's a very interesting algorithm, and with a somewhat delicate analysis. Yeah, hopefully my explanation here is clear. So the utility of the distance to instability algorithm is somewhat interesting, because we get perfect utility with high probability when, in some sense, when the margin is large. And on the other hand, like we get no utility at all when the margin is small, because we simply refuse to answer. Right. So one may argue that how does this compare to the exponential mechanism? Right. It doesn't compare to the exponential mechanism in equal footing unless we can define some kind of utility measure. So I'm designed a homework question series for you to compare the distance to instability and compare its utility to this exponential mechanism, so that you can see like when does it make sense to use one versus another. All right, so let's take a break, and we'll resume at 2:21, and then we'll talk about the proposed test release mechanism, which can be viewed as a generalization of the distance to instability. All right, see you guys in a little bit. Oh, okay. Let's resume the lecture. And during the break, there was an excellent question about how this argument could work through, and I realized that we should have discussed the case A and case B in a slightly different way. So case A should be the case when fx prime is different from f of x, and in this case, it implies that d of x and d of x prime is both 0. Okay, this is by the fact that x and x prime, they are mutually neighbors, and in their neighborhood there exists something else in the neighborhood such that such that fx is different from fx prime, and then which like automatically gives us this, showing that this is 0 delta dp. And the case B, so it doesn't actually just require dx to be not 0. In case B, so the discussion will be f of x prime is equal to f of x. In this case, the d of x could be 0 or could be non-zero is irrelevant, because no matter what the dx is, it is an insensitive function, and we can just add noise to this insensitive function, and the decision becomes post-processing. Right, so this is a much simplified proof. Yeah, which I was discussing the two cases wrongly, like earlier in an earlier part of the lecture. Yeah, I hope this is clarifying. All right. So now let's get to proposed test release. So what if the local sensitivity is not 0? What if it is not like an arbitrary f of x that remains the same, like in all your neighbors and all your neighbors' neighbors and all your neighbors' neighbors' neighbors? Can you still do something meaningful with this idea? So that brings us to the proposed test release. Which requires you to first propose a bound, say a bound beta on the local sensitivity. So for some reason you believe that this beta is gotta be an upper bound of local sensitivity, because if it is not, then maybe you don't want an answer to begin with, right? So you propose this beta, and the second step is to test the validity of this beta. So this is a generalization of the distance to instability function that we talked about earlier. And the previous function is equivalent to choosing this beta to be 0. Okay, so previous function is equivalent to choosing this beta to be 0, but here we can choose this beta to be other to be other numerical values that are larger than 0. Okay, so we add Laplace noise to this distance to not so locally insensitive data sets, x prime, and then we will discuss two cases and return Q of x plus the Laplace noise, where we calibrate the Laplace noise according to this upper bound, the proposed upper bound of the local sensitivity, if d prime is larger than 1 over delta over epsilon, else this is return. I'm not going to answer anything. Okay, so that's the idea of proposed test release. And it can be shown that with the parameter epsilon, delta, and beta, and this algorithm with any such parameters, and this algorithm is true epsilon delta differentially private. We'll see how to generalize the previous analysis of the proof on the distance to instability to this case. Okay, so the case 1, we discussed the case when the local sensitivity of this Q at the data set is larger than beta. So when this is the case, when this is the case, it implies that the distance to stability, the distance to beta instability is equal to 0, and this is because the fact that the local sensitivity of X is larger than beta indicates that this X is within this set itself. Okay, X is within this set itself, and X to itself, the distance of X to itself is equal to 0. Now then d hat will then be just 0 plus this Laplace noise 1 over epsilon, and using the fact that this function again is one sensitive, and using the tail bound of the Laplace random variable, then we know that d hat of X being larger than log 1 over delta over epsilon. So this is a standard tail bound for Laplace random variable. This is equal to delta. Yeah, this is smaller than delta because it's, I think, one-sided. Now, okay, so with that, now let's try working out the definition of epsilon delta differential privacy. So let's say that this algorithm proposed test release is M. So M of X in some set, let's say that this is set set S. Okay, so what is output space first of all? So the output space, let's say that Q is from the space of data set to the real value, and then the output space is a union of this R with this possible choice of I'm not answering. So this is output space. So let's say S is an arbitrary subset of this output space. Okay, so S is an arbitrary measurable set of this output space, and now we can also define. Yeah, we should also define this to be. Wait, is it strictly greater than or strictly greater than? So let's make this strictly. So let's define this event to be E. Okay. And in this case, the probability of this is equal to just S intersect with E complement and intersect with E itself. Okay, because E has low probability, then we know that the second part of this is smaller than delta. And for the first part of it, we know that whenever we intersect with the E complement, and this is already ensuring that the output is equal to perp. It is ensuring that the output is yeah, it is ensuring that the output is equal to perp. So this part is equal to P of M of X. This is smaller than that. This is equal to okay. And because the choice of getting to this perp is a decision that's determined by adding Laplace noise, and by the post-processing principle, this is smaller than e to the power of epsilon mx prime is equal to perp. Okay, and plus just plus delta. And now now let's add this S back, and we can replace this with S intersect with E complement. Okay, we can, because this is the same, this set of S intersect with E complement is the same as just this perp, then I can simply replace this set so that without changing anything. This is equal. Yeah, sorry, it's not equal, it's smaller than, because I applied the definition of epsilon delta differential privacy. And the next step is to use the fact that when I intersect with a set, and it's only making this set smaller, so this is smaller than e to the power of epsilon p of m x prime belonging to S. Then I can drop this intersection with E complement, which shows that altogether shows that, at least in this case, this is epsilon delta dp. Okay, so that's case one. In the other case, when the local sensitivity of X is smaller than beta, right? This means that Qx minus Qx prime absolute value, by the definition of local sensitivity, this is smaller than beta. And then this is saying that the Laplace mechanism that outputs something in R intersect with a perp, right? So this is a composition of two Laplace mechanism. Composition of d hat and adaptive composition of d hat, because the second run depends on the output of d hat. Sometimes it's not run at all. In another case, I'm just adding another Laplace noise. But when I add the Laplace noise in the second time, based on our assumption, the local sensitivity is actually smaller than beta. Therefore, this Qx plus Laplace 1 over epsilon and Qx prime plus Laplace 1 over epsilon. So these two distributions are epsilon indistinguishable. Right? So this is a post-processing. Whether you run this at all is a post-processing of a pure DP mechanism. And whatever you run, if you run it, it's also like epsilon DP. So altogether, so case 2 is 2 epsilon 0 differentially private. So altogether, the larger of 2 epsilon 0 and epsilon delta gives you altogether, it gives you 2 epsilon delta DP, the proposed test release. Right, so it's a direct generalization of the previous analysis. The reason why we get the 2 epsilon is because the final output is now like different, right? So in the previous case, when Qx is equal to Qx prime, then whether you add noise at all, then you get epsilon 0 dp, because it's only coming from this d hat, the post processing of d hat in deciding whether you want to output this or tilde, or just perp. On the other hand, in the proposed test release, the final output could be slightly different, and that contribute to another factor of epsilon in the 2 epsilon dp analysis in the second case. Okay, so is this argument clear? So any questions about this? Okay, no questions. I'll move forward. So yeah, PDR is very useful because we can, if we know how to propose this bound, then we can privately test it, and no matter what the local sensitivity and the smoothness of the local sensitivity looks like, then as long as we can propose such a bound, then it allows us to adapt to some structure of the data set when this structure is actually there. So if we believe that there is such structure in the data set, and this gives us a way of testing this property, and if it passes the differentially private test, then we can just proceed by assuming that this property exists, and with a small probability delta of failure, in which case like we don't really worry that much about the privacy losses anyhow. So one issue about the PTR, so there are two issues with the PTR approaches. The first is that how do I know which beta parameter to choose? So how do I like have a sufficient understanding of the problem without looking at the data before I can know what is the right choice of beta? Right, choosing beta in the data independent way will either be like a little bit too conservative, or it will be inappropriate to the point that I will only be mostly getting perp from the analysis, which like doesn't mean much. And the second issue of the PTR is that, well, we talk about the smooth sensitivity approach being incapable of dealing with non-numerical queries. So this issue is addressed in the case of distance to instability. But when we generalize distance instability to PTR, it seems like we still have to rely on local sensitivity, because in the last step we are adding noise to that query anyhow using the privately tested upper bound of the local sensitivity, right? So can we apply like PTR-like idea to go beyond releasing numerical queries? Okay, so that's two questions that still remain. So we'll spend the rest of the lecture addressing the first question. Okay, like let's motivate that by looking at this example of differentially private release of a graph statistics. Let's say that we're given a graph, and this graph is a sensitive data set. And the goal is that we want to estimate the number of triangles in this graph on the so-called edge differential privacy. So edge differential privacy means that you can add or remove any individual edges, and then the output of this algorithm should remain like epsilon delta indistinguishable. So that's a problem. So what is the global sensitivity of the number of triangles in a graph? Right. So you have a graph that connect that. So you have a 4 nodes graph and 1, 2, 3, 4, 4 edges. So in this graph you have 1 triangle. Right. In more complicated graph, you basically want to find all such triangle shapes and enumerate them. So that's the yeah, so people want to do that in social networks and in all other many other graph analysis. So since we require this graph to be arbitrary, so adding or removing one individual, adding or removing one edge could mean that this edge is making like all these V-shaped object. Like now that we add this edge, and then it suddenly becomes a triangle. But there could also be another node over here that when we add it, it creates 2 additional triangles. There could be a 4th node here that when we add this edge, it creates another triangle. So in total, this can be done for all possible number of edges, all possible number of nodes in this graph. And so the global sensitivity of introducing like 1 additional edge or removing 1 additional edge is a -2. So this is really large, and even if we fix it, and the local sensitivity on the other hand is bounded by the maximum degree of G. So what is the degree? A degree means that how many neighbors do you have on this graph? Right, so you enumerate the number of neighbors for all individual nodes on this graph, and then you get this degree sequence, and the max degree is the largest of them all. So it can be worked out that the local sensitivity of this problem is the maximum degree of G, what if we can add noise proportional to local sensitivity? And we satisfy the same issue of local sensitivity itself, could reveal sensitive information. But in this case, in this case, it can be easily see that the local sensitivity or the maximum degree of this graph G has a bounded global sensitivity. Right. So now we're talking about differentially privately releasing the local sensitivity itself. If we can do that, and then we can construct differentially private upper bounds and lower bounds of the local sensitivity, and that allows us to just add noise according to this privately released upper bound. Okay, so to see that the max degree of G satisfy bounded global sensitivity, we can try just adding one additional edge to this. So adding one additional edge to the graph will introduce two, will make the degree larger, like for the two nodes that this additional edge connects to, right? So it can only affect the max degree by one at most, right? So to say it differently, the local sensitivity itself has a global sensitivity of 1. Okay, so if we write it down, so this means that the local sensitivity, the delta of the local sensitivity of Q itself is 1. Okay, so we can hope to privately release local sensitivity. Okay, so here's a slightly more general extension lemma. It says that if we can provide if we can provide an upper bound, a high probability upper bound to the local sensitivity, yeah, so this delta is a local sensitivity. Yeah, sorry about the notation. So this is, in this case, means local sensitivity of F. So if we can differentially privately release a high probability upper bound of the local sensitivity, this means that with probability 1 minus delta, this will be smaller than the delta tilde of FD. Right, so if we can come up with an algorithm that takes the data and then output a high probability upper bound of the local sensitivity, then we can simply add noise according to this high probability upper bound, and overall, like, it satisfies 2 epsilon delta differential privacy. Okay, so now let's see how this works. So the output, let's say that the output is y and then the delta tilde, right? So this is the output of this algorithm, and we know that delta tilde satisfy epsilon delta dp, and we know is epsilon dp, and we know that this y is equal to f of x plus Laplace, right? So that's the algorithm. So we can, like, take any measurable set of this concatenation of the space. So y and this belong to S1 times S2. So let's say S1 and S2, they are the arbitrary measurable set of the output space. So this given the data set X, and again, let's define this E to be the event such that that happens with high probability. So this being larger than the local sensitivity of F. Oh, okay, so this is a good event. Now we can so notice that this event apply only to S2. So we can just intersect this with S2. and intersect its complement with S2 without changing anything. So this is equal. And using the fact that this E complement happens with small probability according to this condition, and we know that this is smaller than delta. And now under this alternative condition, okay, so under this alternative condition, under E, then this upper bound is always a valid upper bound of the local sensitivity, which means that which means that let's first decompose the first part of this into two parts by just using this conditional expansion of this E. So this is under, yeah, maybe let's write this X to be over here so that we can actually do conditioning. So we'll condition on delta tilde, and if we condition on this, then we can get rid of all these, right? So this is basically Y being inside this XS1, and then multiply with so I'm basically factorizing the joint distribution into the conditional and the marginal. So I just wrote the conditional, now I'm writing the marginal. So the marginal would be this belonging to S2 intersect with E, okay, plus delta, and this is smaller or equal to. Now, using the fact that this delta tilde is epsilon differentially private, I can upper bound this probability with e to the power of epsilon while replacing this x with x prime. So this becomes e to the power of epsilon p x prime, where x prime is a neighbor. Okay, and now on this conditional distribution, and notice that notice that all the cases when this delta tilde is when delta tilde belongs to E, right? So this becomes the this becomes the integral of this over all delta tilde belonging to S2 intersect with E, right? And the delta tilde. And for every one of these, since this is intersecting with E, we know that this is a valid upper bound. So under E, this delta tilde is a valid upper bound of the local sensitivity. Therefore, adding the Laplace noise to this would preserve the neighboring relationships up to e to the power of epsilon. So I can replace this by e to the power of epsilon. Now px replaced with p of x prime, and y belongs to S1 given delta tilde, the delta tilde, and then e to the power of e to the and then multiply with this, and then plus delta. And all these together we can assemble them. Yeah, all these together we can assemble them into p of x prime y, and delta tilde belongs to S1 multiply with S2 intersect with E. But we can also just drop E, because intersecting with anything will make the set smaller. So this is smaller than p of x prime y delta tilde inside x1 times S2 plus delta. I forgot this e to the power of 2 epsilon, e to the power of 2 epsilon. And this altogether shows that this satisfies e to the power 2 epsilon delta differential privacy. Yeah. So for a slightly more general argument, you can check out this paper, which shows that you can just replace everything with epsilon delta dp, and everything is still true. Right. So this is a nice approach to say that we don't actually need to smooth the local sensitivity. We can just privatize it, and if we can privately release an upper bound of the local sensitivity, and then we can add noise according to that local sensitivity while adapting to the data dependent structure. And the privacy is a smoothing property itself, then we don't need anything else to further smooth it. And how do we construct this delta f of d in the previous example? We can simply add noise. Since the global sensitivity is just 1, we can say add Laplace noise to that and construct a tail bound so that we can get a high probability upper bound as what it is required in this lemma. Okay, so that's I guess that's all I wanted to talk about today. Yeah, so we didn't get to talk about the case when the output space is not numerical, which is going to be the first thing that we discuss in the next lecture. And the question is that how do we design data adaptive versions of algorithm that doesn't rely on like noise adding? For instance, we've talked about posterior sampling, objective perturbation, and noisy stochastic gradient descent, and all these differentially private machine learning algorithms, they're not just like simply adding noise to the output. They're more complicated than that, and they depend on other system dependent and data dependent quantities other than just local sensitivity. So we'll talk about how to generalize the idea of proposed test release, and then think about how that can help us to come up with data adaptive and more useful versions of this differentially private machine learning algorithm in the next lecture. Okay, see you guys on Wednesday.